Hello and welcome, EE 32104. This is Professor Hiren Trada. In this video, what I'm titling is Lecture 19A, a series of short videos for today, just to make it more easily digestible. We will begin Chapter 4. So, Chapter 4 is our entry into digital logic circuits. So, logic circuits. So in this short video, what I'm going to do is introduce the concept of digital signals. Okay, digital signals. So far in all of our analysis, we have learned in 201, in 321, we have always dealt with analog signals, right? And when I say signals, signals can be referring to voltage, current, or power. Okay. Typically, we would say it is referring to the voltage, but they could refer to anything. So it's a generic term for all kinds of functions. And of course, it also sometimes is labeled as a function. Okay, so analog signals, if you look at this image right here, this is an arbitrary analog signal right here. Okay, does not have any specific form. It's not a sinusoidal waveform. It is not a square. It is not rectangular, triangular, sawtooth. Does not have any form. Okay, it's simply arbitrary, and it could be representing basically a voice recording. It could be a noise signal. It could be a radio wave signal, wireless signal. It could be anything. But the point is, the value of this function changes with respect to time. Right? It changes with respect to time. So time is always on the x-axis, and amplitude or magnitude or the value of the function is on the y-axis. On the right here, we have a representation of a digital signal. A digital signal, again, it is still a waveform, but it is in the form of a rectangular pulse. It's a form of a rectangular pulse. And typically, a digital signal may have a 50% duty cycle. When I say duty cycle, it means the time or the ratio for which it is on and for which it is off. When I say on and off, well, let's move this here. Duty cycle refers to the ratio, whether it is on and off. On and off simply means some sort of positive value and some sort of negative value. It may not be a negative value. It could just be 0 volts, but basically this is the highest value and this indicates the lowest value. That is the first thing you should keep in mind when we talk about digital. Okay. So in this function, in this signal that we show here, we have, again, time on the x-axis, how the signal is behaving with respect to time. And here we see the amplitude. The amplitude of the signal, or the value of the signal, is +1 for the time period 0 to t. So the first time period, it has a value of 1. And we could say that that 1 indicates a on state. Okay, the 1 indicates an on state. Then when we move on to the time period, second time period, between t and 2t, we see it has a negative value, -a. And so we can represent this as being off. And then again, time 2t and beyond, it has a value of +a. And we can represent that as on. So logically speaking, this only has 2 values. It only has an on value or off value. And those are represented mathematically as 1 and 0. 1 and 0. Okay, and that's how we represent it as mathematically. Now, Circuits, of course, do not have, circuits run on voltages and currents. They do not have the ability to distinguish between logic 0, logic 1, logic high. It is the words and the equations, that we as humans need to use to perform our calculations. Circuits are still running on voltages and currents. Circuits are still working the way we learned about in 201 and earlier in 321. Okay, all of this digital logic values on, off, it's all for us humans to perform analysis. So always keep that in mind. Okay, so the advantages of digital signal. What is the advantage? Well, let's look at this on the left here. This is the analog signal. Let's say this is what we are trying to transmit, whether it's wired transmission or wireless, does not matter. Let's say we are trying to send this from point A to point B. Okay, trying to send this signal from transmit from A to B. Now, when transmission occurs, there's always noise that is picked up. Okay, noise is basically any unwanted signal. Noise, electrical noise, is any unwanted signal. So any unwanted signal in our desired output is basically termed as electrical noise. So here, this is the same signal with some noise in it. And you can see that it has the same shape or similar shape for the most part, except now the actual amplitude has changed, right? So let's take this as an example. Right at the origin, the value of that signal is supposed to be 0. Right at the origin, value is supposed to be 0. Yet here, because of the noise, it is not equal to 0. Okay, and the same thing as we go along this path right here, you can see all along the path there is a lot of noise. And so if you're trying to reproduce this, let's say perhaps this is a music recording or audio recording, then there's a lot of noise, arbitrary noise, that is reproduced in your speakers. Let's take the case of the digital signal. In the digital signal, if it picks up noise, well, the amplitude has now changed, right? The amplitude has changed, the value has changed, yet we can still say the system is on for the first time period and off for the second and on again for the third and fourth. So even though there is noise in there, the system recognizes what the output should look like. Okay, it recognizes the output and reproduces, it recognizes the signal and it reproduces the output faithfully as similar to the input. And so that is one big advantage of digital signals versus analog. Okay, we can reduce or completely eliminate any noise signal that might be picked up during the transmission. Okay, so digital advantage is huge in terms of rejecting noise signals. Now, you may ask, how does that, how could that work? Wouldn't the noise affect the system? Well, that's the thing. The concept of using digital logic is based on using our devices such as the BJT transistors, FETs, MOSFETs. These are all kinds of transistors, and all those transistors are operated as switches. Okay, operate as switches. So they are operated either in on mode or off mode, which is basically saturation or cutoff. Okay, So even if there is unwanted noise in there, the unwanted noise is not big enough to actually deviate the state of operation. So if a transistor is supposed to be on, that extra noise that is picked up is not going to affect the operation of the switch. Hence the noise margins. Noise margins are basically defined in the system as basically the noise tolerance that a system can withstand. Okay, so we have to define in a system, we have to define what we will call as logic 1 and what we will call as logic 0. So in terms of the voltages, let's say this is ground level, right? This is ground level, which is 0. So all of this is 0 volts. And we would have to have a clear demarcation. So input low voltage at this level, let's call it VIL, and this would be VIH. Now VDD is typically 5 volts. In modern digital circuits, it's also 3.3 volts. So the lower the voltage, the less is the power requirement, and less is the heat that is being dissipated. Okay, so let's stick with 5 volts. So if we say that our logic signal varies from 0 to 5, we can take 1/3 of that signal and define it as logic 1. Meaning if the system sees, let's say for example, 0 to 5 volts, 0 to 5 volts logic, we would define, let's say for instance, 3.5 volts to 5 volts signal as logic 1. And then we can define 0 volts to 1.5 volts as logic 0. Anything else in between would be undefined. So 1.5 volts to 3.5 volts would be undefined. Okay, undefined region. So if your circuit is functioning and your digital signal is supposed to output 5 volts, let's say there's a noise signal coming in and your 5 volts drops to 4.5 because of the noise. Well, if it drops to 4.5, your noise margin still allows this to be recognized as digital logic high or digital logic 1. Okay, and so hence a drop in the voltage does not translate into lost information. Same thing with the other side. You know, if there is a signal that is being transmitted, it's supposed to be 0 volts, but instead of being 0, instead of 0 volts, it now climbs to 1.1 volt. Well, in digital, it would still be recognized as 0 volts. I'm sorry, not 0 volts, as logic 0. Okay, logic 0. Now, depending on the requirements of your application, the noise margin could be as high as you want or as low as you want, right? If you want to create a very sensitive system, meaning you do not want any deviation from your, logic zeros and ones value, you would try to keep the undefined region as small as possible, right? And so any deviation from your values for logic 0 and logic 1, even if it's very high, it does not matter because your undefined region is small, your noise margin is very large, right? Noise margin is very large. So any deviation from there does not really matter. Your system can pick up even the smallest of signals without any issues, without any problems. Now, depending on the application, of course, you might want the undefined region very large. And if that's the case, then your noise margin is very, very small. Okay, like we have shown here on the right. So again, it depends on the application, but for the most parts, it is better to have a very high noise margin. Okay, very high noise margin. All right. So we talked about logic 0 and logic 1. This is a representation of a typical digital signal. And because there are only two values that it can take, let's say here, this is logic 1, and we say it's on. This is logic 0, say it's off. And then it alternates, right? Alternates. So logic 1 is on, logic 0 is off. And because this can take only two values, we refer to these two values as states. So two states. Two states. Those two states are on or off. There is no in between. It's like a light switch. Okay. There is no dimmer in there. A light switch is a digital representation. It only has two states. It is either on or it is off. Now the light still works. The light switch still works on voltage and current, but it only has two states. So that is a digital representation of a analog application. Okay. So when you have in your electronic system, you have only two states, on or off. We say it's a binary representation system, only has two states. That is what binary means. Binary is very important because that is what all of logic analysis is based on. And so I really like these next two memes. This is a very famous saying, at least in electrical engineering, that there are 10 kinds of people in the world: those who understand binary and those who don't. And if you don't understand this now, you will in the next video. This is very funny. I really like it. Again, as I said, if you don't understand this now, you will when we actually look at binary numbers. Okay. So binary number system is based on the logic that there is only two numbers in the system, only a 0 and a 1. And we will look at the entire binary number system, perform mathematical operations or logical operations using binary number systems, and see how we can use it to analyze our digital logic circuits. And we will do that in the next video. So this current video will stop right here, and we'll pick up again from here for a binary number system.